Euclidean Geometry, Rider 8. There's the usual reminder on thought processes for doing geometric riders, solving geometric problems. It's been in many a video up to now in this series. I'll keep using that, plus a bit more of the strategy used for the ratio proportion riders. So here we are. Here's our example for rider 8. We have a tangent to a circle and RP equals RC. First we'll prove that ACPR is a cyclic quadrilateral. So we are now thinking, what if ACPR is cyclic? And there I've drawn in the situation that I think is easiest for that. I'll explain why in a moment. What if that is the case? Well, A1 is the exterior angle, P1 and 2 is the interior opposite angle. So A1 would equal P1 and 2. There are many other options for proving it cyclic. C1 is equal to R1 and 2, and then we have 4 different angles on the same segment possibilities where we could use the converse to prove that those 4 points are concyclic. But I have chosen the one there because I already have P1 and 2 equal to C3. So P1 and 2 is already equal to something else. So I can already got the option and the potential for one of those domino things where A equals B and B equals C, therefore A equals C. An axiom. So let's go through this one. What is A1 equal to? There's your hint. There's your tangent. If you know your theorems, you'll see it straight away. Tangent chord C4 equals A1. Tan chord or alternate segment theorem or angle and alternate segment, depending on which way you've been taught. Is C3 equal to C4? Pretty clearly, vertically opposite angles. And of course we know that P1 and 2 equals C3. There it is there. So therefore A1 equals P1 and 2, and we have our cyclic quadrilateral. So we go through our thought process. A1 equals C4. Tan chord. C4 equals C3, vertically opposite. C3 equals P1 and 2, angles opposite equal sides, or isosceles triangle. And therefore we have A1 equaling P1 and 2. Which gives us our cyclic quad by converse exterior angle cyclic quad. Remember the theorem says cyclic, therefore angles equal. This is saying angles equal, therefore cyclic. Next part, prove similarity. Now in proving similarity, there are 3 angles we have to prove equal. So I look at it and say, what is likely to be the way? I'm not waiting for the geometry to come to me. I'm saying, well, which angles are likely to be equal to one another? And we go from there. So C1 would equal R1 and 2, and this is why I've said C1 and R1 and 2, because I can see that already. Here's our cyclic quad. I know my theorems. So those are equal. Exterior angle cyclic quad. So we look at B1 and B1, B and P2. So we say, well, what is B equal to? B is equal to C2. There we are, tan chord. Now we say, is C2 equal to P2? And there we have our bow tie for angles in the same segment. Yes, angles in the same segment. So we now have B equal to P2. And of course, A1 equals A3. The last remaining angles have to be equal by angle sum triangle. So we can do our proof, setting it out in the same way as a congruent triangle proof in triangle CBA, RPA, 1, 2, 3, therefore similar in the correct order. C1 equals R1 and 2, exterior angle cyclic quad. Now we do our little mini proof within this proof. B equals C2, tan chord. C2 equals P2, angles in the same segment, therefore B equals P2. And finally, A1 and A3 are equal by angle sum triangle. the remaining angles in those two triangles. So therefore we have triangle CBA similar to triangle RPA. And notice angle C equals angle R, angle B equals angle P, and angle A1 equals angle A3. Yeah, sorry, I had to look, I'm getting old. Next part. Prove that that is the case. Now there are a couple of ways we can go about it. There is a long way around, and I'll show you. I'm not going to do the long way around, but I'll show you how we get there. So I take that statement there that I have to prove, and I put it into the proportion form where it's easier to work with for similar triangles or proportional intercept theorem. I do my vertical test, and out of it I get an R, a C, and a B, and an R, an A, and a C, and those two triangles come up. This blue one and this big red one. And they do look similar. Have a look. There's a common angle, and the C2 is equal to B by tan chord, so they are similar. But I'll have to prove more similar triangles. So let me have a look the other way. Trying horizontally, RCA, CBA. And those don't look similar at all. I mean, this is an obtuse angle. There's no obtuse angle there. Obviously, it might not be drawn to scale, but even so, I don't think so. But we keep in mind that RP equals RC. And that being the case, there's an RC. So what I'm going to do is I'm going to replace RC with the equal RP. And now you will notice that we have exactly the two triangles that I've proven similar before. So that's the way we're going to go. Therefore, RP over CB equals RA over CA. I need RP, so RP, it must go over CB, first second over first second, equals RA first third. And why did I choose RA? Because there is an RA there. It must go over CA, and I just hope it fits in. And then I write it. I say, well, RP equals RC, so therefore that's the case. And that means that we have proven exactly what is required. The third example now. Back into the proportion form, we do a vertical test, and straight away we get those coming up. So we may as well have proved them before. Hey, but never mind. We have those two triangles similar, and it's pretty easy to see why. I've already talked about that. So let's go into the similarity proof. In those triangles, 1, R1 is common. C2 equals B. Star equals star. Tan chord, angle and alternate segment theorem. And the remaining angle, A2 and 3 equals remaining angle C1 and 2 by angle sum triangle. Therefore, triangles similar. Once again, correct order. R equals R, common. C in the one equals B in the other, and A in the one equals C in the other. Because from there we can now obtain. We want RB. So I say, well, there's an RB, so I must put RB over RC. So RB, RC, so then I need a CB on the other side. There's CB, and it must go over AC. There we are. And from there, it follows what we have to prove. Notice, similar triangles proven, just for the fussy marker, in case you want to take a mark off you. Finally, we have to prove that RC squared equals RA times RB. And notice the hence is a big hint, and it's also an instruction. If it says hence or otherwise, it's just a hint, because you can do it whatever way you like, but it says, look what we've done. Hence here says, use what we've done. You have to use what we've done. Prove that RC squared equals RA times RB. So now I can't go back and prove similarity in any other way. I have to use here. There's no RC squared, but there is an RC and there is an RC. So what I'm going to do is, I'm going to say, well, D we know RC, C, D we know we can find RC, and now why don't we just multiply what they're equal to, and then hope that it works out. That's the whole bit about don't wait for geometry to come to you. We're trying strategies. So there, in 1, we've proven that. In C, in D, we've proven that, which means that RC equals. Now I'm going to multiply 1 and 2. And have a look. AC's cancel. CB's cancel. I'm left with RARB, which is exactly what is required.